Okay, hopefully we should have a new stream. Everything should be going on okay now. If you can log on to that new stream, and I expect people will start making a comment to say that the new stream is live. But until then, what I'm going to go through here is I'm going to say that, so we're starting the third chapter. The third chapter of the book, Aviation or Aeronautical Engineering, represents about 16% of the HSC course. We've already done about 65% of the HSC course, and really the course is pretty light compared to the last two chapters. We've done the bulk of the difficult stuff so far. So what I'm going to look at now is I'm going to go to the textbook before I go to the syllabus, and I'm going to say that, okay, so if we look at, there's a little bit of chapter 2 that we still had to do in terms of communications, but I think communications I'm going to do as a separate video. So that's looking at section views and some definitions of spot facing and things like that. But for us at the moment, and threads and bolts at this point are well and truly stuff that we've covered. So in terms of the chapter 3, what we have is, as always, we have 4 parts. We have the scope of the profession, which includes things like historical context and impacts of the innovation and legal ethical implications, the engineering profession. So beyond that, we then go on to materials. So this part here is all the, and this is really where we're going to focus, is on today's lesson, is on introductions, where we look at different planes through history. But then we're going to go on to mechanics and hydraulics. So with mechanics, the first part is we're going to find out about parts of the plane. So I usually refer to this as controlling flight when I write this as a HSC question, or sorry, an exam question or something. Beyond that, we do look at a little bit about the mechanics of that, but that's not anything I would lose too much sleep over. Ultimately, this comes down to really just friction questions, and so if you've understood the sliding questions, the boat questions that I call them, in friction, this will be very, very familiar. So that's the bulk of what we do in terms of mechanics. Then we do have a little bit of stuff about the nature of flight, so what I call lift, generating lift. So we talk about the principles of how a wing actually does generate lift, things like the Bernoulli's principle, but that is only part of the answer. So there's what we talk about as the classical theory of flight, which is Bernoulli's principle, and then we have more complicated systems. I have some videos that will talk about that, we'll discuss that. We talk about engine systems, so different types of propulsion, and that's a topic that's a part of this definitely places where I look to put in questions. After that, there's a little bit of fluids. Now, the fluids is mostly a revision of Pascal's principle, and this here might look a little bit new. We did discuss this last year. There's only ever been one HSC question on this formula. So again, I'll discuss it and I'll tell you what that question is, but we've looked at it before, nothing we'd worry too much about. The main thing that we look at is the applications of aeronautical instruments. Specifically, we look at pitot tubes, which is how we airspeed indicators, and then altimeters, which tell us about how. So there we go, altimeters, which how high the plane is, what the altitude of the plane is. When we get into materials, there's a little bit about testing, so magnetic particle testing, gamma ray testing. I do try to talk about testing right back in year 11, so I like to sort of cover testing over and over again, but not a whole lot there. Just remember that gamma rays are stronger than X-ray testing, so I remember that as Hulk was generated through gamma rays, and Hulk is the strongest there is. So there's an episode where Hulk fights Wolverine, and yeah, he smashes Wolverine because he's way stronger than Wolverine. Okay, so because Wolverine's an X-Man, if that wasn't clear. Okay, so the main materials we look at here is aluminium. Now, we've already talked about aluminium, these series of aluminiums. So we're mostly interested in the heat treatable aluminiums, which is the 2000, 6000 and 7000 series. In order to remember those, I remember that the 2000 series is copper, the 6000 series is magnesium and silicon, and then the 7000 series is zinc and magnesium. Okay, so we talk about alclad specifically is worth mentioning. Aluminium, lithium alloys. I'm not going to go through everything now. This is just to give the overview. They talk about compression molding as just a fabrication method, and transfer molding. Yeah, just okay. But what we're really interested in is hand layup and vacuum layup. So this is how we use fiber reinforced polymers, and when we use these. We have two main methods. So either we can just lay out the fiberglass, or in this case it can also be carbon fiber reinforced polymers, or it can be glass fiber reinforced polymers. Whichever one it is, we can lay out sheets and then we apply the resin just with like a brush, or we can use something called an autoclave, and we put it in a bag called a pre-preg and put it together. We've got videos on that. We'll look at that later. Okay, the next thing we have is composites. So composites we look at, and I think we've talked a little bit about this before. So we've already just talked there about reinforced polymers, but so the glass and carbon. And then we have aramid fibers, FML, fiber metal laminates. The main one that we're interested in is glare. Glare is what's used in the A380, but there are others. Yeah, anyway, so then we have MMC, so we'll talk about those as well. Okay, a little bit about corrosion, pit and crevice corrosion. There's not a lot there generally we don't have a whole lot of questions on that. And stress corrosion. Now, the hard part in terms of drawing in this topic is developments. Now, developments, you might be familiar with these as nets. So that's the term you would use in primary school, is to talk about the net of a shape. We use the term the development of a shape. And the development of a cube is six squares. That's we're pretty familiar with. That should be fairly obvious. But for a shape like this, the development is a bit trickier. So that is something, and it's actually something really, really hard to do in recordings. I have tried doing recordings, but it's actually something that really needs to be seen in person. But we'll see how we go. So that is the development for that shape. That's what the net would look like. It doesn't have a top or a bottom. So the bottom would be a long rectangle, that's not here, and the top would be sort of a square, that's not shown. Okay, so that I'm pretty sure is the end of this chapter. So you can see that, I know I went through that quickly, but we'll see that there's not a heap there that we need to worry about. Just a comment that if someone could just chuck out a comment, just so I know that things are actually recording and the things running live, that would make me feel a little bit better. But in the meantime, what I'll do, and I know this seems repetitious, but sometimes setting the context for things is useful. So okay. So telecommunications went a little bit too far. So this is the syllabus, and now these are pretty much the same. We've seen, I think, almost all of those outcomes already by this point, so that's not an issue there. What we have is, in terms of the 4 main points, so we have scope of the profession. I am not going to read through all these dot points today. I will go through them, but if we look at the high level, the scope of the profession is often very similar for each thing. And this is part of what you're going to do for your aeronautical engineering report. So your assignment is going to consider how has aviation affected Australia, and what are the career prospects, what are the legal and ethical implications of aeronautical engineering. That's what we're going to discuss in today's lesson in detail in a second. But before we get on to that, okay, so historical and social influence. Then we're going to go, okay, so mechanics, we have the fundamental flight mechanics. So the 4 main forces, this again, we see things like, if you replace lift with the normal force, and we have drag, we'll replace that with friction. It basically looks just like regular friction. In terms of lift to drag ratio, that's an important consideration, that how we talk about the effectiveness of a plane. That's how we evaluate how good a plane is. The angle of attack is the angle of the plane, and that's very important. If we have too steep an angle, the plane can crash, and we'll look at case studies where that's happened. We're going to do a lot of calculations. Most of the calculations in this course, in this chapter, will come from there. Okay, in terms of the nature of how we generate lift, we're going to look at Bernoulli's principle in a fairly vague term, right? We're not going to go into that in as much detail as we might in, say, university. But we're going to look at the Venturi effect and how we generate lift, and we're going to look at the fact that the classical theory of flight is actually not technically correct. It's a contributing factor, but in fact, when we're dealing with fluids, fluids are very complicated, and we only need to know a HSC level. We don't need to know a university or a postgraduate degree level understanding. Okay, we do cover bending again. Now, bending is a bit of a funny one so there's a bending question in the last HSC, and I overheard some teachers complaining about the appropriateness of bending being applied to planes when the concepts of bending are a little bit unusual. But it is an important concept as part of aeronautical engineering, in the fact that when we look at things like the early biplanes, the reason why biplanes were produced is because the materials weren't there to give long spans like modern gliders, and instead by having two wings, it was a way of increasing the area of the plane without increasing the wingspan, and therefore inducing more bending. So bending is definitely, I think, relevant here, and you should be prepared for bending questions. You probably aren't going to get one this year, but you should be prepared for the fact that there have been plenty of them. Okay, propulsion. I think propulsion's pretty easy. The names are a little bit convoluted now. So the thing that you have to remember is the example that a student has told me before is that the names of these systems get less impressive as they get better. So turboprop sounds more impressive than turbofan, but turbofans are the modern planes that we use the most. And turbojets sound cooler again, and they're the oldest and the least used. Okay, so we will look I'll talk a little bit about RAM and scram. Turboprops and rockets. We'll talk a little bit about rockets, but we're not as concerned about that. Okay, so moving on to fluid dynamics. Yeah, we don't really. We mainly focus here for me. Hydrostatic pressure is fine, and that's really important if hydrostatic pressure is really important for people who work in hydrology. So people who design the pipes for your sewers and things, and for your water supply. But for planes, the main thing we're worried about is those two instruments we talked about: the pitot, or the airspeed indicator, and the altimeter. Just a comment: I can see the comments that the image is a little bit blurry. Luckily for you guys, I'm only talking about documents that you should be able to see yourself. So if when you go through this later, you can open that in another window or something to see what I'm talking about. I will also zoom in when I get to the next, when I actually start going through things properly. Okay, in terms of testing, we talk about dye penetrant testing. We've already talked about that before in the book. All of those things are already in our big testing mega post, the one with my mate Sam Rockwell. And aluminium alloys we've already discussed a little bit about, but we're really just going to focus on that precipitation hardening, the 2000, 6000, 7000 series aluminium. That should sound familiar to you guys, and I'm hoping that you're hearing all this saying, hey, a lot of this stuff should sound really familiar. The lift and drag is the most new, but it's actually very similar to what we've done in friction. Okay, so looking at, so structural, that's just heat treatment of alloys. All of that stuff would be, I call precipitation hardening. Thermosetting polymers. Okay, so we're going to look at mainly hand layup and vacuum layup for that is something that we haven't looked at before, but I've got some good resources, some good videos that you can see that being done, and that's good. Composites, where the main ones we're interested in is in the FMLs, the main one being glare, but we will talk about a few others as well. Corrosion, we're just talking about specific corrosion to aviation, pit and crevice, and stress corrosion. And then in communication, the big thing we didn't write an engineering report. We have to do an engineering report, so that's here. Collaborative work practices will be interesting, but I guess we'll find a way of making that work. And the main thing we're interested here is development, transition pieces, so which we've looked at. Okay, so having looked at the syllabus there, that should give us some confidence that really we're in a very, very good place. To be where we are before the start of term 2 is like we're further ahead than I've been with any of my classes, and I really am expecting us to do very well. Okay, so now that we've got that, let's open Copeland's book. Hopefully he won't sue me for putting this on the internet. Okay, so I'm not going to read this verbatim because that's no value to anyone. You guys can read, and you can read faster than I can speak. So when we're talking about the nature and scope of aeronautical engineering, well, typically what we're interested in is the people who design and produce planes, and the people who maintain and operate planes and airports. That's the key that we're looking at. Now, there are obviously things beyond that. So in terms of, I just said planes, well, planes is a very specific term. So that refers to fixed-wing aircraft. But there's also rotary wing aircraft, so that would be helicopters. And these days, aeronautical engineering can really apply to things like drones. It can apply to, so it's very similar to aerospace. So aerospace is rockets and satellites, and it's very closely related to a lot of fields. So everything from, like, say, Formula One racing vehicles, a lot of the aerodynamics that we use in aviation has very strong links to the principles of Formula One racing. But things like, hoverboats aren't really that big a deal, but hovercraft, they would be something that is entering into a combination of nautical and aeronautical engineering. So that's the main considerations we'd be looking at. Things like also blimps and weather balloons and that sort of stuff. But really the main focus we're looking at, and especially in this course, absolutely our focus is going to be strictly fixed-wing planes, but increasingly drones as they become more important in society, as well as just an interesting technological innovation. They are something that you should be mindful of as well. Okay, so current projects and innovations. So when this book was being written, I think this book's about 10 years old now, or at least this text might be 10 years old. The Dreamliner was the big thing in development. 15 years ago, the Airbus A380 was launched, and that was I think it's the biggest passenger plane designed. And it has seen the end of its production life. So it hasn't seen the end of its service life. They'll probably still be flying for like another 30 years or something, but somewhere. But they're seeing the end of their production life. So the main reason for that is because of changes in flight habits. So I have some videos that will talk about those changes in flight habits. This is passenger-driven incentives. Is that generally speaking, in the past, so 15 years ago, if you were going to Europe from Australia, you would probably be traveling with one or two major carriers, and you would typically go to a place like, so for instance, Qantas only flew to London and Frankfurt. So if you wanted to go to Paris, well, you would choose one of those two cities, and London and Frankfurt actually probably about equally distant to Paris. But you would go from there, and then you would take a connecting flight to your destination, or a train if you were really keen. Or a boat if you're Greta. Anyway, so these planes have been replaced with people increasingly. So even when you went to Frankfurt, you would stop over in one of three destinations. You would stop over in Singapore, Hong Kong, or Bangkok. These days, increasingly, we have stopovers in Dubai, and there are cultural reasons why people stop over in Dubai, cultural and political reasons. And then from Dubai, you can then fly directly to Paris or to Rome or wherever it is that you actually want to go to. So you may even be able to fly directly to, say, smaller cities like Lyon to save yourself having to take that train, that connecting train. Or, I don't know, like to go to Sicily, for instance, or if you wanted to go to Warsaw, that sort of thing. You wouldn't have to. You'd be able to fly directly. So I'll quickly talk about the, just in case I never think to come back to this, why Dubai and what are the political and cultural aspects? Well, the fact is that Dubai is very oil rich, and Dubai, for historical reasons, is very concerned about what happens when the oil runs out. So they have been positioning themselves to create as many future-proof industries, so tourism being one of them, but aviation being another. I guess those two even go hand in hand, and aviation, particularly the fact that aviation uses a lot of fuel, that by having a lot of people travel via Dubai, that it's future-proofs their economy, so that if oil runs out, they still have something. Or if oil stops being a valuable commodity, they still have something, rather. The political aspect of this is that Dubai, because of their oil wealth, they can afford to have very, very low taxes. So it's very difficult for companies like, say, Qantas or Air New Zealand or whatever to compete with Emirates or Etihad Airlines. Anyway, look, that's a little out of my specialization, so I'm not going to go down that rabbit hole too far, but that's my understanding. Okay, so current projects and innovations. So these days, you probably wouldn't say the Dreamliner was a big innovation. What I would say these days, so things that when I've talked about innovations, drones are definitely an innovative area of aeronautical engineering. This is something where we have a lot of work happening, and a lot of the new applications for drones are really actually improving all the time. We have just things, and this is where we're talking about like tangential sizes. When I was looking at some resources, things like the Hyperloop that Elon Musk and others are talking about, where it's an alternative form of transport, but it really does rely on a lot of the same principles as aviation in terms of reducing drag and aerodynamics. Not so much the lift aspects, but a lot of the other similar factors. The other areas that I would say are important in terms of planes, chartered flight. So this is very, very rich people having smaller planes is seeing greater use. Things like the JSF, the Joint Strike Fighter. So what's that? The F-35 is a relatively new technology in fighter planes. So we'll talk in a minute about how military usually has a pretty big driver of aviation, and it's definitely something you should write in your aeronautical report. Okay, so health and safety matters. So civilian and military or aeronautical engineers can be exposed to dangers. Okay, well that's true of every field. Like right now as a teacher, we're balancing risks. But okay, so what are the main risks to health? Well, in terms of exposure, the biggest risk to ground crew and to pilots is noise. I would say that was probably the biggest risk. Being deafened by, even if only partially deafened by the very loud sounds of the engines, and reducing the sound is an important part of aeronautical innovation. So people, not only is everyone trying to make their planes more fuel efficient, but everyone is also trying to make their planes quieter. So that's a big area of research at the moment. Beyond that, okay, obviously also everyone wants to prevent their planes from flying. So we'll look at for instance, the case study of the 737 MAX and what went wrong there. But also things like the increases in autopilots. So autopilots are obviously really important and absolutely save people's lives, but over-reliance on autopilots can create problems. So we'll look at that in the future, as there's a 99% Invisible podcast called Children of the Magenta, which we'll cover that. So falling out of the sky is a problem, but in terms of statistics, it's actually much lower than it would be for other fields. So if we're comparing this to, say, roadside work, well, there's a lot lower risk of injury, and that's mainly because of maintenance. Something we will talk about later is factor of safety, and the fact is that the factor of safety on planes is much, much lower than the factor of safety for cars or for structures, and that's because we need our planes to be very, very light, and in order to improve fuel efficiency. And how we compensate for that lower factor of safety is we compensate for that with higher, much higher maintenance, and that's how we manage to get those advantages. So the next thing is training the profession. So aeronautical engineering is a field that people can study, and there is career opportunities in Australia and overseas. So the biggest employer, I think, is the Defence Force. So you can go through ADFA, and so the Defence Force Academy. They are the biggest. I think they have the biggest course. But yeah, there are different places where you can study aeronautical engineering. Often people will do mechanical engineering and then specialize in aeronautical engineering as a postgraduate qualification. In terms of design and maintenance and operation, Qantas and airports are the two names that come to mind. We also have Rex, which may or may not survive the 2020 economic situation, but that's regional airline, a regional Australian airline. We have things like the Flying Doctors. We have air freight being an increasing part of aviation, so an increasing amount of air traffic is going into, maybe not as a percentage, but at least as a tonnage. We have a lot more air freight happening now in the world of Amazon. So the main place in the States for people working in aviation is working for companies like Boeing or Lockheed. From what I'm led to believe, they're fairly big producers. So Lockheed is military, so that they're military aviation. So they're focusing on planes and on fighters and bombers and that sort of stuff, missiles, guided missiles and that sort of stuff. I've only ever seen like one episode of the TV show Medium, but I'm pretty sure her husband was a aeronautical engineer, and he worked for Lockheed, and it kept him up at night. Anyway, unique technologies. Well, I'm going to take just a break for 30 seconds because I have to help out someone else. Just 1 second. Okay, and we're back. So, thanks, Cameron. Okay, technology is unique to the profession. Well, the big one is that that they use turbines or propellers. So, so turbines are used for ships and power stations, but in terms of using a turbine to produce thrust, and that thrust then generating subsequent lift, is a thing. So, a lot of things start in aviation or things like aerospace, and then they trickle down so that they make their way into the industry. So, for instance, in the Apollo missions were in the 60s, and that led to a lot of technologies that were introduced in the 70s. Things like Teflon, which is a coating that we now use on our pots and pans, pots and pans. But we have technologies that were developed for other purposes and then find their way into other fields. So, aluminium alloys that were initially developed for aviation then find their applications in other contexts. Okay, so when we're talking about materials, there's four main considerations we're interested in. So the strength to weight ratio, so not so much how strong it is, but how strong it is divided by its self weight. formability, so how readily it can be made into complex shapes, durability, and corrosion resistance. Now, I would say durability and corrosion resistance are the same thing, but what I guess they're looking at there is, in terms of durability, is things like fatigue resistance, whereas corrosion resistance is we really want to avoid corrosion. So that's where aluminium and fiber reinforced polymers or carbon fiber reinforced polymers are increasingly used. But we will look at the composition of materials. So aluminium and those composites are pretty commonly used now. Okay, I'll let you read the rest of that. Okay, so the Eurofighter Typhoon is the I think the F-35. That's an innovation that we're looking at in terms of modern planes that are currently seeing development and introduction into the field. Okay, so legal and ethical implications. So there are, like here they're talking about patents, and so patents for the one person who also does design technology is something we talk a fair bit about in protecting your work. So I'll use the example of, for instance, if you were developing a vaccine, there has to be a financial incentive for people to spend their time. There might be some people who love their jobs so much that they're willing to sacrifice their own family's well-being in order to work for free. But most people do hope that what they can do is not only enjoy it, but also manage to support themselves. And in this context, the intellectual properties are that generally we take the attitude that we like the idea of being able to prevent other people from benefiting from our research. We don't want to spend billions of dollars developing technology and then find that someone else comes along and copies that technology. I mentioned before that 99% invisible, so I think I've gone another 3 minutes without mentioning it. They had one talking about the production of titanium oxide, which is where we get the white chemical. And well, actually, they have two. The same episode's called "His Darkest Materials," I think is the name of the episode, and they talk about the exclusive rights for artists to use a material called Vantablack, which was originally used for the aerospace industry, and then they talk about this titanium white, where there was a sting operation where I believe it was the Chinese were trying to take the manufacturing process and sell it to China. So that's something I can put you onto, but there's plenty of other cases where we want to try and protect the intellectual property of people who have spent billions of dollars researching things. So that's what they talk about there. They use the example of Volvo. So Volvo is the company that developed the three-point seatbelts, and they chose not to patent their research because they valued saving lives over the financial gain that they would have. And that probably gave them good PR. Whether or not that was a wise decision is not for me to make that call. So in terms of legal and ethical implications, I think that Copeland really misses what I would say the key considerations, which is that what are our legal and ethical implications in terms of warfare? So planes really are so heavily linked with warfare, and so much of their development came from their application in military settings. That wasn't the word I was looking for, but I can't think of it at the moment. So the two obvious examples would be Hiroshima and Nagasaki, and the bombing of Dresden, where aviation was used in arguably an egregious manner, so that this technology was used in a way that was unprecedented and arguably excessive use of force. So that's a very an easy example to point to for ethics. But we have a lot of other examples we can think about. We can talk about what are the ethics of building planes near, or building airports near other people's or near existing properties. We can talk about the ethics of carbon emissions. So I made a joke earlier about Greta and her taking the boat to go to the UN, but the fact is that from a carbon perspective, it uses considerably more carbon to fly somewhere than it does to take a train. And for Australians who live on an island on sort of the far side of the world, that makes pushes decisions a little bit more towards aviation. But for people who live in Europe, trains are only mildly more inconvenient, but they're drastically more environmentally friendly. So they're just a few quick ethical considerations. Legal considerations are often of a similar nature, that we have the patents that we just mentioned earlier. So patents combine both of these two concepts, but patents protect legal protections on the use of things. But in terms of legal implications, if we have things like a carbon tax, which was suggested over 10 years ago by the Gillard government, that would be a law. That would be once that law is passed, that would affect aviation and their operations, in that they would have to find a way of paying for the increase in carbon dioxide that they produce into the atmosphere. And similar things like the flight times. So planes typically aren't allowed to fly before 6:30 or something, but under certain circumstances they can. So for instance, if they're transporting like the flying doctors, for instance, they're allowed to override that requirement. So there's some legal implications that you can look at there, and that they do have similarities. So ethics of noise, and then the legal requirements that companies have to work around with. Okay, so engineers as managers. So they talk about managers in two senses of the word. First, there's the design process, overseeing the project, and then there's also working together to bring together teams. So the hierarchy. So I guess one is terms of managing process, and the other one is terms of managing people, is probably how I would phrase that. So when we talk about managing process, the things that if we go way back to the very first or second lesson that I had with you guys, I talked about engineers in terms of we design, manage, and operate. So you might be someone who designs the building, and then there's someone who produces that building, and then there's the third person who maintains that building. This is true for roads as well. So you'd be a road designer, and then there's someone who goes out and builds the road, and then there's the council or the state authority who goes and patches that road and maintains that road and makes sure that it's operating. And I think that in terms of university students, I think the prestige definitely goes in that order of design, produce, operate. But as I've said many times before, that all you need to do is turn off your water for a day to appreciate that water is really important, and that things like sanitation has absolutely saved more lives than modern medicine has. So, but no one thanks the guy who's responsible for your water supply the same way that you thank a doctor who operates you for your tumor. Okay, so in terms of managing people, so generally you'll have someone who takes the final responsibility. So the contract will be overseen by one person. You generally don't want to have a committee of 2 or 3 people who might argue. You want to be able to talk to one person who's in charge. But then they will have sub-disciplines below that. So this is true of all three stages. There'll be one person who's in charge of the operation of Sydney Airport. There's one person who's in charge of, or who would have been in charge of, say, the design of the A380. And there's one person who'd be in charge of the production of those things, the production of that aircraft or that structure. So the big thing when we're looking at management is we're generally interested in time and money, and then safety and environment are also very important considerations. Arguably, you can say safety is the most important because it only takes one death on site to wipe out a lot of your profit anyway. But that's something you will find in your professional life that is juggled a little bit. Okay, so we've already talked about that. Okay, relationships with the community. So we've talked about volume and noise as being really important. Yeah, okay, so this first paragraph, which I didn't address, is that aviation has a really important impact on the quality of life, particularly for people in Australia, in terms of our access to goods from overseas, and Australia being a very multicultural society. We have a lot of people who work overseas and a lot of people who have come from overseas and often want to travel home to visit their families. Now, so noise is a big factor for aviation. I would also say the building of airports is a really important consideration in that they, on one hand, produce a lot of employment, but at the same time, no one wants to live next to an airport. You want to live just close enough to an airport. And there's the military aspect, which we talked about there. So when you say that the engineer is merely fulfilling a request from government authorities, well, I mean, only following orders is an argument that did not work very well for people in the Nuremberg trials. So I'll leave that to you. I mean, again, I mentioned the episode of Medium that I talked about before, but it's not really it's my place to suggest that idea, and it's your place to think about what that means for you. Okay, so now we're going to talk about history for, however long. Okay, so I'm going to go through this fairly quickly. I'm not going to go through this in detail. I'm just going to talk about some key dot points, and I might have another video where I go through this in greater detail, but for the moment I really want to focus on the high end, and I'll let you guys read this. So initially, generally most people would start, and if you guys were in the classroom, I'd point to my picture, which is right in the middle of the room, of the Wright Flyer developed in 1903. That's generally considered to be the start of modern aviation. Now, there are things that existed before that. I have balloon flight by I can't see the date here, but the Montgolfier brothers, I believe is what their name was. I think it was like the 18-something, so I can't read the date from here. And so, yeah, hot air balloons have been used for a fairly long time. I think I have a video that I can show you guys. So if I go here, this guy, he is an engineering studies teacher, and I can provide links to this guy talking. His first video barely only talks about only just gets up to modern flight. I think it's up to World War One or something like that. But he spent some time talking about the Chinese use of hot air balloons and kites and various other things. But he talks a little bit about like Da Vinci. He talks about how Da Vinci had drawings, but I don't think they were being put into practice. I have watched videos where people have tried to recreate modern versions of Da Vinci's drawings, and they've had to make fairly advanced, rather not advanced, fairly substantial variations. So before the Wright Flyer, there were people who worked on before. I can't remember the guy's name. This guy here, he talks about it. Hargrave? I don't know, Hargrave's the Australian dude, but I think there was someone else as well. Who did work on developments, and the Wright brothers were actually inspired. Actually, I'll go to your notes. That's too far, actually. Go. I'm glad that all this will be in the video. Where are these pictures? Here we go. Okay, so if you look at this, here's 3 different videos that address the early stages of the history of flight. So if you click on this video, they talk about the guy who inspired the Wright brothers. And often we think about, because the Wright brothers owned a bicycle store, we often think about their Wright Flyer as being something that was pedal powered. And I think the very, very first flight that only went sort of 700 meters was in fact pedal powered. But very quickly they had developed, and I think they'd previously developed a lightweight engine which they used for their sustained flight. And the Wright brothers developed a plane that was able to take off, fly in a circuit, and land. They didn't quite make the so the U.S. government had a prize for the first person to demonstrate just what I said, which is to take off and land. They didn't claim that prize, but I think they ended up having sort of the last laugh, and they made a fair bit of money. This guy talks about the broader picture of he gets up to jet engines and talks about World War II planes. The Boeing case study I think is pretty good because I think they're very indicative of the aviation industry generally. Okay, so I'm going to go back to here. Probably don't need this one open now. It's just going to go away. Okay, so the thing is that the Wright brothers, they and those 3 videos. This video here talks about the 3 principles of flight. So roll, pitch, and yaw, generally the 3 as they're described. And so they worked on a way of producing roll, pitch, and yaw to control their flight. You can watch the video, which will explain that a little bit better. And we have plenty of resources that I will eventually talk about to help you remember that. So that's up here. So that's to help you remember yaw because it looks like jaws, and I have other ones for roll and ailerons and pitch, which involves the tail, which is on the elevator. Elevators, which are on the tail, rather. Okay. So the French also claim, and I think the Brazilians also claim they were first to produce flight. That sort of stuff doesn't really bother me too much. If I was in an exam, I would write the Wright brothers because history is written by the victors. Okay. Okay, look, I can see the comment. I'm going to sum up very quickly and then I'll let it go. Okay, so that follow-up, I will post a follow-up video which talks about the World War I flyers, and I've already talked a little bit about that. But then we have the jet age. So World War War I planes were pretty simplistic. The video talks a little bit too much for my liking about the nature of how machine guns worked and how they developed from people initially just shooting out of the side of the plane to eventually automated machine guns that would fire through the propeller. But really, the big innovations in aviation really came in World War II. So both the helicopter and the jet engine. From the jet engine, this is where we start seeing some pictures, right? So the Gloucester Meteor, and then we start seeing the F111, which has swing wings, which I thought were the coolest things when I was a kid. We don't really like those anymore. We didn't have canards, these little wings here. They're called canards, which is French for duck, but they're really just little wings. Then we're interested in the Harriers, which have vertical takeoff and landing, so we'll look at all of that stuff later. In terms of aviation, we have jet aircraft, more jet aircraft, the 747, that's the important one. The Concorde we'll definitely talk about in terms of why it failed, and then we have like really big planes that were developed by the Russians, and then the A380, which was also a failure. And then we talk about finally the Dreamliner, the 787, and why that was a success. Okay, yeah, Cameron, I like that comment. Okay, so that's enough of an overview. I'll supplement that stuff with some videos as resources. I really don't like the idea of reading this. I like just pointing out the couple of details. So I'm going to set the homework for you guys that you're going to read that, which I've already done actually. So I think that'll be enough for today, and have a good one. I don't see you tomorrow. I will see you in 2 days, and we'll see if this works. We'll continue. Bye.